Hey guys, this is David. In the first lecture of this mechanism course, I want to talk about the concept of degree of freedom and how this concept can facilitate further analysis. First, let's go through the definition of degree of freedom. It is the minimum number of coordinates required to describe the independent motion of the system. In order to give you a clear picture of what it is, let's examine how many degrees of freedom does a rigid body in a plane have together. For a rigid body in a plane, there are three kinds of independent motion, which are translation in x and y direction and rotation about the z-axis. So now we know that we need at least three coordinates x, y, and theta to describe the motion of a rigid body in a plane, and by definition, it means that a rigid body in a plane has 3 degrees of freedom. However, say now we have a system with two rigid bodies connected together by a joint, then how many degrees of freedom does this system have? In order to answer this question, another important concept besides degree of freedom should be discussed, which is kinematic constraints. Kinematic constraints, by definition, are constraints between rigid bodies that results in reducing the degree of freedom of a system. In planar mechanisms, there are two commonly seen kinematic constraints. The first one is revolute joint, or R joint in short. As you can observe in this example, the rigid body is constrained by a R joint, which allows only rotation about the point XO, YO, and results in reducing 2 degrees of freedom of the rigid body. This result can also be described using these two equations, or what we call constraint equations. So now it is clear that a R joint reduces 2 degrees of freedom of a system, and the degree of freedom of this system reduces from 3 to 1. Now let's look at the second type of kinematic constraints, the translational joint, or T joint in short. In this example, a slider is translating on the ground, or in other words, the slider is constrained by a T joint. To be more specific, the T joint only allows the slider to have translation in x direction, which in other words means that the slider cannot have translation in y direction nor rotation relative to the ground, and therefore results in reducing 2 degrees of freedom of the slider. And again, this result can be described using two constraint equations shown here. Since we know that the slider is translating on a plane with height equals to YO, and that the slider cannot rotate with respect to the ground. So now it is clear that a T joint reduces 2 degrees of freedom of a system, and the degree of freedom of this system reduces from 3 to 1. From the previous examples, we see that the degree of freedom of both systems reduced to 1. In fact, single degree of freedom system plays a big role in the analysis of mechanisms. The importance of a single degree of freedom system, or single DOF system, is that after assigning any one of the coordinates used to describe the motion of the system, all the other coordinates can be determined. This may seem to be confusing at first, so now let's demonstrate it with the example from R joint. Here is the example we have seen in revolute joint. And as we have explained, this is a single DOF system. In this example, XO, YO are known, but the coordinates x, y, theta are unknowns. In order to show that it is possible to determine all other coordinates after any one of the coordinates is assigned for a single DOF system, let's now assume that the x-coordinate of the rigid body is assigned. With the assigned x-coordinate, y and theta can be determined by the equations shown here, which proves that we are able to solve for all other coordinates once x is assigned. Analogously, once y is assigned, x and theta can be determined by the equations shown here, which again proves that we are able to solve for all other coordinates once y is assigned. Last, assume that theta is assigned, then both x and y can then be directly determined by these two constraint equations. Now we have shown the fact that for a single DOF system, once a coordinate is assigned, all the other coordinates can be determined. Also note that the assigned coordinate matters since it affects the uniqueness of the solution. In this example, assigning theta is much preferred than x and y because assigning x and y results in more than one solution. The other reason why single DOF system is worth mentioned is because most planar mechanisms are single DOF system, such as rocker crank mechanism and slider crank mechanism. You may be wondering why these mechanisms are single DOF system. Therefore, now let's take a look at the rocker crank mechanism first. For a rocker crank mechanism, there are 4 bars and 4 revolute joints. Also, recall the fact that each bar has 3 degrees of freedom under the assumption that the bars are rigid body, and each revolute joint will reduce 2 degrees of freedom of the system. Note that the bar down here, or sometimes we just call it ground, cannot move at all. Therefore, the total degree of freedom of the system is 1. Next, for a slider crank mechanism, there are 3 bars and a slider and 3 revolute joints and a translational joint. Recall the fact that each translational joint will reduce 2 degrees of freedom of the system and the ground doesn't move at all. Therefore, the total degree of freedom of the system is again 1. Now we have shown that these 2 planar mechanisms are single DOF system. In the next video, we will talk about the goal of kinematic analysis and show you how to do displacement analysis of these systems using vector method. See you next time.